And, or, you know, in a human brain, there's layers in your neocortex that are looking at different frequencies of information. You know, like the low layers are looking at tiny little details in your, say, in your visual field, whereas like the higher layers are looking at, you know, things like looking for a face or looking for like, you know, recognizable shape. That's a tree, that's a woman, that's a this. So, so these abstraction layers, you know, this is, you know, we kind of take it for granted that we're naturally divide even the sciences into abstraction layers, right? There's the physicists who are looking at tiny little things, and there's the chemists who are looking at like groups of those tiny things. And then there's the, you know, if you're in a body, then you have like tissue specialists, and then you have maybe like holistic doctors that are looking at the body as a whole. And then you have, you know, sociologists who are looking at, you know, many people interacting together. So you can kind of zoom out and zoom in on anything, and you know, you zoom in on something and it splits into a bunch of pieces, and you zoom out and everything kind of gloms together. And so you know, but another important piece of this brain is that if it's going to make a decision, there's lots of things it could do. Presumably it has lots of muscles, lots of things it could, actions it could execute. So it needs a way of sorting them so it can pick the best one. And when we say best one, we mean the best estimated one. You don't ever really know what your actions are going to result in. So you make an estimate, a prediction about the future, and you have to evaluate. And so in machine learning, you call this evaluation, you call it an objective function. It's basically a function that tells you how right were you, or how much closer to your goal did you get. So, you know, in the human brain, that could be like, you know, how much pleasure did that bring you? Or in a company, it could be, how much money did you make? Or if it's like a B Corp, it could be, you know, how much money did you make times or plus, you know, how many people were, you know, how many poor people were benefited, or whatever the metric is. And so this, and then all of that so it synthesizes all this data, and then it evaluates it, and then it makes a decision based on it, whatever it thinks is going to maximize its objective function, whatever your goal is in life, right? Your brain is always, if you tell your brain something important, it's going to automatically start, you know, evaluating things relative to that. So then here's the muscles, and this is, you know, it can be a physical human muscle. It could also be in a robot. It would be like drive a motor, you know, it could be like, you know, spin your wheels and go forward. Maybe like lift the arms of the robot. In an organization, it could be like, okay, we're going to deploy the sales team, or we're going to release a new product, or, you know, we're going to place this ad, or we're going to buy off this politician. And then if it were like a trading bot, it would be like, okay, you need to buy Bitcoin. Oh no, now you need to short Bitcoin. You know, and so it's basically these actions that you know, are intended to improve the objective function in some way. And then the whole thing keeps looping around, right? Then you reevaluate the environment, collect the data, particularly if you're trying to behave intelligently, you want to collect data about the effectiveness of your own actions. And this is something that I mean, large organizations have trouble with. It's particularly, you know, something like as large as a government or some of these bigger corporations. A lot of times the people who make the decisions actually have no idea about the effectiveness of their decisions. You know, you might imagine a world where every bill that goes through Congress has an attached sort of objective function to it. Be like, how are we going to know whether this bill was successful? How are we going to measure that? Are we going to do a study in 5 years and see, did this actually reduce crime? And how are we going to fund that? So, and likewise in companies, you know, sometimes management, everybody's just telling them what they want to hear, right? Everyone like kind of fudges the data a little bit to make it a little bit pretty for their boss, and then he fudges everything to make it pretty for his boss, and then this is putting noise into the sensors, and so as the information travels through the abstraction layers, you know, the executives are being lied to sometimes, and it's really nobody's fault. And so anyway, so that's the big picture here. I wanted to also relate this, you know, in a kind of more mathematical way, what this looks like in machine learning or artificial and natural intelligence. There's kind of two broad categories of machine learning here: the supervised and unsupervised. And the idea is that you've got this brain, and you're trying to train this brain to make good predictions, or which could also result in good decisions. And so supervised means when you're sort of feeding it pre-labeled data, meaning you give it a bunch of examples, be like, this is a good decision, this was a bad decision, or this is a cat, this is a dog, or this was when the Bitcoin price went up, and this one was when the Bitcoin price went down, right? So you have all these sort of pre-labeled data that then is encoded in an abstract way into the brain that allows it to act on data that it's never seen before. And we'll dive into, there's kind of two broad ways of looking at that: regression and classification. But the other way of doing it is unsupervised, where you kind of you give the computer the data, but you don't give it the answers. It's almost more of a creative approach, where you let the computer come up with its own labels. And so the kind of prototypical unsupervised learning algorithm type is called a clustering algorithm. It's where you have a bunch of stuff, and then it kind of groups it together and basically labels it, like, these are the red ones, and these are the green ones, and these are the blue ones. And let's just go ahead and look at that. So this is another way to look at it, is that so this is just like another way of looking at that same picture earlier, where we have, this is the sensors on the left, the inputs are the sensors, and the outputs are the muscles, or the motors, actuators. And then here's the brain, right? So what is this brain really doing? I think if we think back in school, there were some people who did well in school, but maybe they were really just kind of memorizing the data, memorizing the academic material. And so maybe they had difficulty using it later. Maybe they forgot it very quickly. And in machine learning, what this is called is overfitting. It's where you basically just get the machine to memorize the data, which makes it really accurate on the data that you trained it on, and very inaccurate on data that it's never seen before. And so that's not really the goal of learning. The goal of learning is to give a few examples, and you want people to generalize from that, right? So it's like, I put my hand on the stove when I was a kid, and I burned my hand, and it hurt really bad. Now, do I need to put my hand on the stove again because now it's a different time of day? It's a different stove. My hand looks different. I'm older, right? All these variables have changed. Do I need to put my hand on the stove again to test that out? No, of course not, right? The brain's pretty good at generalizing these kinds of situations. And there's also such a thing as overgeneralizing. Sometimes we turn it into a kind of rule and it's not always applicable. So that's, another way of looking at this is that it's compressing the data, right? You've had terabytes or petabytes of data come through your brain in your lifetime, and that's, if you want to behave intelligently, you can't just sift through that all the time. I mean, we just don't. It's not practical to try to go look through it all the time. So we want to kind of compress that down into a model that is smaller, so we can act more quickly and more efficiently. So another way of looking at this machine learning thing is it's developing a compression of the data. It's a lossy compression. You're not remembering all the data, but it allows you to generalize. And so we're gonna look at that a little bit more closely. So this is what they call regression. I mean, it's honestly, this name is really kind of confusing. So, don't try to make too much sense of it. But the idea is when you take statistics 101, the first thing they probably show you at some point is this least squares regression line, right? So the idea is you have all this data here on the left, all these little data points, and then you want to find the line that minimizes the different distance between the line and the points, right? So another way of saying that is you're minimizing the error, where basically the error is your objective function. You're trying to minimize your error or maximize your accuracy. And so this blue line, if you look, the blue line actually doesn't go through that many of the data points. It actually misses most of them. But what's helpful about this blue line is that it's pretty close. And also, if you see it, if you put an input on the x-axis here that this line has never seen before, if there's no gray data point that corresponds to that x value, it doesn't matter. You can still guess what it is. And that's what generalization is here. There's an input I've never seen before, right? The world is always changing. There's an input I've never seen before, but how do I relate it to the other inputs in a way that makes me give a good guess on what's the appropriate action here? The Y value here is the output. That's the decision you make based on that. And just to so this is like the sort of most basic form. You know, you're applying a linear model to, like, you know, say this is temperature readings. You know, that's something that a lot of scientists have done, and you know, temperature is really complex, and so sometimes things aren't linear. Sometimes they're wobbly. Sometimes they're exponential. There's all kinds of varieties of relationships here. So I just want to show another example here on the right, that you can have multiple inputs, multiple variables, right? Heterogeneous. One of these could be from the eyes, one of these could be from the ears, right? And then the output here is a surface, right? And the surface is more complex than a line. It's more complex than a plane, but it's still quite a bit simpler than this messy cloud of blue data points. So this is what it's all about. We're trying to make a simpler model, replace a complex body of information with a simpler one that we can reason about. And you don't want to make it too simple, because then you know, start creating illusions and being too rigid. But you know, here's a simple example. You might have a data set of a bunch of people, you know, that, you know, you have their age, their height, their sex, and their weight, and then you try to predict their disease risk. And it turns out, you know, for some diseases, this is actually, like, you don't actually need much more than this to make a fairly good prediction, better than just randomly guessing. You know, some diseases are more complex and maybe touch a different abstraction layer of human society. So you're always, you know, sometimes the input data doesn't actually have any information about the output, and so we have to think about that. Are we collecting the right data that has signal in it? Maybe if you look at their astrology chart, you know, and that was what the input here is, maybe there's some information in there, maybe there's not. Maybe there's some signal, but it's really tiny. So yes, this is an example. The point is that this disease risk is, so the reason this is regression, this is disease risk, that's kind of like a probability. It's like a number between 0 and 1. It's like a floating point. It's not it's continuous. It's not discrete. And so there's, you know, on the other hand, you could have classification, which is the other way of doing it, where it's discrete. So it'd be, meaning that there's like a finite number of categories that we're going to pigeonhole things into. So, so in this case, you could take the same inputs and you could try to guess someone's political party. And there's only, like, what, in the US, there's 2 political parties, maybe 1. And so this is like, you know, this would be bucketing, is another term people use here. So this is basically the same idea, but the output is instead of being a continuum, it's discrete answers. So it could be true, false. And sometimes you just take your regression and then you set some threshold and you say, like, okay, if it's above 50%, I'm going to say it's, yes, high risk. And if it's below 50%, I'm going to say low risk. So you can always take a continuum and bucket from there. And that's actually how internally most of these classification systems actually work. So anyway, so here's an example of what it looks like with unsupervised learning. So this is clustering. This is where you don't give the computer the answer. You just give it the data and ask it to organize it. And so this is an example here. Like, if you look on the left, there's at the bottom, there's all these like individual data points, right? And you can kind of see as you move up in the y-axis, the data points are getting clumped together. Nearby points get clumped together, and then the clumps can also be clumped together. And so this corresponds in your brain. You think about, like, when you learn to read, what do? First, you look at, I mean, if you have a phonetic language like English, first you learn the letters. And then later, as you continue reading, you start learning clumps of letters, right? And then when we get good at reading, you stop seeing individual letters for the most part. You'll see words, or sometimes you'll start to see phrases, right? And so you can, you know, people can learn to read really fast because they're not looking at the individual letters. They've moved up in this hierarchy of abstractions so that they're looking at clusters of letters. And And so this is, you know, this is zooming out, zooming in sort of thing. And you know, there's different personality types. Sometimes people, how am I doing on time? We got 7 minutes. Okay. Sometimes people are much better at zooming in. I mean, we've all met, like, you know, the sort of Aspie engineer type or mathematician type who likes looking at the details and kind of like finds something interesting and curious and dives into it and forgets what he's doing, forgets that there's other people, forgets that, like, maybe he needs to eat, right? That's an extreme case, you know, but that's sort of like, some people are better at zooming in and some people are better at zooming out. They don't like details. They can't handle all these, like, this little fuzz, but when they can zoom out and be kind of like, you know, like the dyslexic Steve Jobs, right? You can see these brilliant business models and opportunities that connect a million different things. And so this is a pretty useful concept, even if you're not going to be doing data science yourself. And you can see on the right here, look, there's all these little data points, and then they got colored. They got colored by this, and this was a clustering algorithm called t-SNE, which you don't really need to know that, but basically it grouped these data points into clusters. And you think these clusters right here are basically labels. It's a classification, but it's kind of auto classification. So like it clustered all these together and it called them purple. Now the fact that they're purple is just for visualization, is not really relevant. The point is that they got grouped into the same group. So if you see something else that's similar to those, let's give it the same label, right? So it's all about making sense of past data to make effective decisions in the future, right? So the climate, or, you know, how your stomach feels at any point of the day, or, you know, what the Bitcoin price is doing today, all these things are constantly changing. They're constantly changing. So we need to summarize our past data in some way at an abstraction layer that isn't too general and isn't too rigid and overfit. And so that's what's going on here, is just grouping these data points together. So okay, so I'm gonna take a little bit of a left turn and then we can, it looks like I got 5 minutes, huh? Anyway, this is just some art you can make with machine learning. This is something I made where basically you get this neural network that's good at labeling images, and then you can kind of like hyperactivate one of the neurons in one of the layers and ask it basically, what do you see in this picture? And so this one, you know, you see this beautiful photo of the buildings, but then you can ask this neuron, like, hey, what are you seeing? Well, and it starts hallucinating into the image. It starts hallucinating. It was looking at windows. Now it's seeing windows in the sky and the water, right? It's all windows here. So that was like kind of the window neuron for this image. So it's pretty interesting. Here's some recommended reading if you're interested in this kind of stuff. John Lilly was a brilliant cyberneticist. He did a lot of far out stuff. He invented the flotation tank. Prometheus Rising is more of a layman's kind of like, you know, less technical kind of approach to kind of programming your own brain. A very brilliant author there. And then the Raja Yoga Sutras by Patanjali is actually really, has a lot of really good stuff in it. I had no idea how deep yoga was until I picked up this book. So, so what I'd like to do now is open it up for questions. Unfortunately, we only have about 3 minutes, so let's get our, I'll get the chat back here. Oh, stop share, is that what it is? Chat, there we go. All right. Any questions, guys? You can also, I think, just turn off your mic. Maybe, I don't know if that's possible.
It was good talk. It was good talk.
Thanks, Aiden. Have we met before?
No, we haven't. No.
Okay.
I guess I have one question.
Okay.
It's like, okay, natural intelligence, AI, natural intelligence. I like that term. But like, where do you view it in terms of like, in terms of human intelligence and in terms of where we are with AI? How far are we from human intelligence in what we've got in AI, or natural intelligence, as we call it, which is a better term, I agree. But like, like a 0 to 100%, like where are we?
It's an interesting question. I mean, one of the things about these sort of AI systems is that they're very, like, you give them a different objective function and they learn different stuff, right? So you could give it an objective function that essentially rewards it for doing really stupid stuff,
Right.
like maybe causing fights or something.
Or
And
looking at windows or whatever.
right, yeah. So I think, you know, in terms of, you know, there's advantages and disadvantages for both systems. For the organic system, we have a lot of flexibility that these machines really don't have. I mean, if you're a data scientist, you end up spending most of your time wrangling the data. You get to do the fun machine learning stuff like 5% of your time. It's like, oh, there's missing data. Oh, this format is wrong. Oh, this, like, you know, we need to normalize this column so it's comparable with this column. I mean, it's a lot. It's a big mess of it's not that fun. I mean, it's very,
Right.
it feels very
Yeah. Like
um,
they're very
would you,
narrow, I guess. So right. So like, yeah. I mean, like that's they're very narrow in what they can do. So I mean, just I know it's a stupid question, right? Like, where are we?
no.
Where
I
are
think the
we on
missing
the goal
piece is
to
the
onto?
missing piece is that the human brains are very good at networking with each other. So it's not, you know, it's not like, let's compare one gigantic supercomputer system with one human brain. It's like, let's look at the collection of supercomputers and AI systems and how well they work together compared to the human brain as a whole, like as in the planet. You know, some people think of humans as the kind of neocortex of the planet. And when you get a bunch of, like, you know, people together that really understand each other, they can enter in a group flow where they're essentially sharing thoughts. They kind of act as like a big brain. So it's 12:30, so I think I'm unfortunately out of time. But yeah, feel free to reach out if you want to talk about this stuff more.
Good talk anyway. Thank you for that.
Yeah, likewise. All right, I'll turn it over to who's next here. Is it Atia? I think she was coming in. Somebody's going to talk about herbs, antiviral herbs. Chris Brignola. Okay. Okay, great. Well, let's. Do I need to do something to? Maybe I need to. Maybe I need to turn it over somehow. Maybe I need to stop my video. Maybe that's how I do it.
So thank you so much for joining this session on how to harness your sexual energy for more creativity, and just not just for creativity, but just generally for a fuller and more juicier life. So I just want to clarify a couple of points that I'm going to be making. I'll have a couple of slides throughout this, but not too many, so you'll just have to listen to my voice and gesticulations. So when we talk about creativity, I don't just mean the arts. So I just want to clarify that I don't just mean you know, becoming a better artist or picking up a paintbrush and being able to draw better or to make a beautiful piece of music. Those can be great channels for creativity, and if you already have those, it can tend to heighten it. But what I mean by creativity is anything that you are pursuing with your energy right now, any way that you are channeling that energy. And then I just want to clarify, what do I mean by sexual energy? So I love to refer to it, and you might have heard this before, as life force energy. So it's literally the energy that we use for creating life, right? And when that is the case,